computer and share screen. Okay, so now today we'll just keep going with our little project and apply what we've learned, and hopefully slideshow from beginning. Okay, now we are going to look at these perimeter beams, and what I want you to keep in mind is that I don't know, you don't see this on your drawing, but right here, okay, right here we have these things that will eventually have to get installed, okay, and these things are called sag rods, okay. Oops, sorry, let me go back. Last viewed. Okay, so these things are called sag rods. What happens is that when you put these members down, okay, these members here, okay, let me just give you an appreciation of what's happening. Okay, these are normally channels that we use to create the girts, and basically this is the channel, and the channel is always placed with the strong axis perpendicular to the wind. So that means that the wind is blowing this way, and the strong axis, where the two flanges are, the strong axis. And what happens is that this is the strong axis and this is the weak axis, and basically these things are fairly weak along the weak axes, and when you place them, they tend to sag, okay? So since they're sagging, what you do is you put these sag rods, you basically attach the sag rod to the top of the perimeter beam here. You attach the sag rod, and that the guy will use this to straighten the thing. It's like, you know, to compensate for, you know, it's like instead of cambering your things about the weak axis, all you're going to do is you're going to put these sag rods, and what these guys do with the sag rods, it tends to hold these things straight, and then once the wall is installed and attached to these girts, the sag rods basically almost don't serve any more purpose, but they're there. And what these sag rods are simply threaded rods. Okay, they're basically threaded rods, and this is what they look like. Okay, oops, sorry. I'm trying to find my, I know I have put here, there you go. Okay, so these, like I said, so these are the sag rods, and basically they, you know, like you make a hole at the top flange of the perimeter beam here. You bring this rod down, and then you have this threaded part of the rod, and all they do is they lift. They put the girt relatively straight. They have a nut here, okay, and that's all these things. So now you know, so that's what these things do. They tend to be used to make sure that all our girts that tend to sag under their, you know, under their own weight, that you can put them nice and straight, so when they come to apply the wall, they'll stay nice and straight. And you know, it's more, you know, like I in terms of strength, they don't necessarily do anything. It's not going to affect the strength of the member. It's just that aesthetically, people like to see things built relatively straight, and that's what these things are. So they're regular steel rods that are threaded at the ends, and then of course you can put a washer, you can put a nut, but you know, depending on the size of the hole, and all you do is basically, you know, use the threaded part to be able to lift. And of course, you put one on one girt. If you have a series of girts, then this one would go and support the second girt. So the second girt gets support up to here, then this is transferred here, and this gets transferred to your perimeter beam. So that's what this is showing you here. So that's what sag rods are. And you're going to have to show these on your drawings, and you'll see this next week, but that's what they are. And then people say, well, what size are they? They're pretty standard, like 1/2 inch diameter, 5/8 inch diameter. They're pretty standard rods, you know, and there's, as a matter of fact, this is one company that, you know, actually manufactures these things. I can't seem to find, oops. Okay, so that's what these things are. Now, because these things are supporting, because these things are supporting a dead load onto this beam, you should make an allowance for a dead load, because what is a dead load? A dead load is the self-weight of the member plus any permanent construction that is going to be supported by the thing. And of course, these things are fairly permanent. Therefore, these two members here will contribute to the dead load. And you kind of allow for that when you're doing your analysis, and you make an allowance. So if what we're going to do now for the perimeter beams, you'll notice that, okay, this is one column, here's the other column, you have a wind column, okay? And normally what happens is that if I draw an elevation on this side, okay, I'm drawing an elevation of this, I have my column here. Well, I'll draw the column the way you see it. I have my column here. I have my column here, okay? So this beam would go right across here like this, okay? And then we are going to learn how to design the connection from the beam to the column, from the beam to the column. And here where the wind column is, it's really right underneath, just almost like a girder system. It's underneath, okay? And we'll talk about this next week. This is called a cap plate. So basically what happens is that this becomes a continuous member, supported here, supported there, and supported there. And now the span is, this is 5 meters. So basically what happens here is that, and of course, these will have concentrated loads from the open web steel joist. And of course, what happens here is, because this is continuous, the bending moment, okay, is like this. And because the bending moment goes from positive to negative, we have another unbraced length here, and so on and so on. And of course, we will use the Excel spreadsheet to make sure that this meets our design requirements, okay? So as far, excuse me, as far as a perimeter beam goes, well, like I said, you can't do nothing in real life unless you look at your geometry. So for the long side, now I break this down into two, okay, I call perimeter beams long side. In other words, the long plan dimension, okay, long plan dimension, and then the short one. So you know which ones I'm referring to. And of course, if you look at your project, okay, because these are all the same all the way through, all I need to do is design one of them. And whatever size I come up for this, you're going to put it there, you're going to put it there, you're going to put it there, you're going to put it there. And because these are exactly the same, you're going to put it there, you're going to put it there, you're going to put it there, put it there, put it there. So one beam design is going to give you the size for all the perimeter beams on the long side. And then on the short side, well, when we get there, we'll talk about it. But on the short side, you have to be careful because you have this one here, okay? Okay. On the short side, you have to be careful when you design the column, because you take this one for the design of the beam, but then when it comes to the columns, you have to decide whether the load from your girder is much higher than the load from the column, and we'll worry about that when we get to columns. So don't worry about that. And that's when we're going to be worrying about designing the exterior columns. So now, so when you model this, you simply, in your ADA, you're going to be putting a pin support there, a roller and a roller. Now, if you happen to be putting a pin, guys, it's going to give you very, very similar results, okay? So as far as, so you pin one support, put a roller. And then, of course, these are the concentrated loads that come from the joist onto your perimeter beam, okay? So, and these are the loads. Now, I would suggest you start, like, what I like to do is I know this from experience, so I like to oversize my preliminary choice so I can compensate for the self-weight of the beam. So this way, if I come with something smaller, I've already compensated for the self-weight, and therefore I know that when I put the other one in, I'm only going to get slightly lower values for the forces. So I do suggest when you're modeling this on ADA, you should end up with a W410 by 39, okay? And then after that, once you've modeled it, of course, you have to worry about your loads. So the superimposed dead loads, this doesn't change. We're using 1 kPa for the superimposed dead loads. And of course, for the snow loads, we're using 2.5 kPa. The only thing that changes here is, of course, the tributary area that's the tributary area that goes from the joist that goes and imposes itself on this beam. So therefore, the tributary area becomes slightly different. And of course, since these things are all equally spaced, this tributary area is the same as this tributary area, and so on and so on. So the only thing that changes here is the size of the tributary area. And therefore, what I'm going to do is, of course, the tributary area here is the spacing times half the span. So therefore, it's 2 times 9 divided by 2. I have 9 square meters in there. And therefore, all that load, when it comes to transfer at this point here, in other words, I have a pressure here that multiplied by this area, that will be the concentrated load there. And therefore, for the superimposed dead load, that would be 9 kilonewtons. And then for the snow load, that would be 22.5 kilonewtons. So that's the loads I would be placing on this thing. And of course, I always use the service loads or the specified load. And then in the load combination is where I modify the load factors and be able to get my design load. So with ADA, you always use your specified loads, and in the combinations, you make sure that you use the appropriate factors. So this would be multiplied by 1.25. This would be multiplied by 1.5. In other words, this is load combination number 3. And now that we have this, so in other words, all you have to worry about is making sure you apply these 2 forces along this member here. And of course, 2 meters, 4 meters, 6 meters, 8 meters. You'll notice I don't care. I really don't care about the loads coming here because that's going to get supported by the column. I don't care about the load. That's going to get supported by the column. So the only ones that are going to be affecting the forces in the beam are these 4, and therefore I'm only going to worry about applying these 4 forces. Okay. The reason here, when we did the Gerber girder, because I'm going to use those values to design this column here, and therefore that's why I also put it here at the reaction area, because I wanted to make sure that that included the force for my design, my column design, and that's why I did it here. But here I really don't care, and therefore I'm only applying it the ones that are going to be affecting the beams. Okay, now, once I did that, of course, now here is all I did here. And guys, I do suggest you do this, okay? I just, like, this is where that sag rod was going to come down and support that girt and then support the other girt and sand. So I just put 1.5 kilonewtons here, okay? And I'm sure I've overestimated the weight of those girts, but I'd rather be on the safe side, and therefore this is just an assumed value. And when we're going to be designing the girts, if we're really concerned, if I was doing this as a real project, once I've designed the girts, I would definitely know what the weight of this girt is. And then from the weight, I would be able to calculate what is the amount of force that's being applied right in the center. And then I can go back and check if this assumed value was okay. In other words, did I overestimate the dead load from these girts? And if I didn't, I would go modify this value of my ADA and see if it has a real bearing on my results. So this is just to compensate. And of course, this is exactly halfway across the span. This is where you would put them, because you would want to support the girts where they sag the most, which is at mid-span. And just make an allowance of about 1.5 kilonewtons. And this is for the girts, okay? And of course, the girts is a permanent load that's being supported by this member, and therefore it would be considered a superimposed dead load. So that's that. Now, and of course, the snow load, we said it was 22.5. So I put 22.5, 22.5, 22.5, 22.5. Then, of course, once you've put in your load cases, you applied your loads. And then, of course, your load combination would be 1.25 times your dead load, 1.25 times your superimposed dead load, and 1.5 times your snow load. That's the only combination. And then, of course, you should have one for serviceability, because once you've sized your member, you should come back, change your member size, and check the deflection and see if you don't exceed that L over 360 or L over 240, whatever is the deflection criteria for that project. Don't go less than L over 240 for a roof, okay? And if you keep to L over 360, that's even better. So that's your snow load. And now, once you run your analysis from ADA, of course, I've already done this. This is what you're going to see. You're going to see your shear diagram, okay? And you're going to see your moment diagram. So this is going to be, for example, if you get a value of 70.6 here for your shear, and you get a value of 72.3 for your moment, then you're on the right track. And like I said, I might have made a mistake, okay? But if this is what you get, you're on the right track. And then once you've got these values here, okay, like I said, what I do is I go, and because here, I talked about this in the Gerber, and I'll talk about this here, because all of a sudden the tension is on this side here, The tension is on this side. And then at this point here, the tension is on that side. Since the compression part of the beam here is not supported, I have to consider this to be the unbraced length of the whole beam, okay? So it's very similar to what we did on the Excel spreadsheet for the Gerber girders, except here we don't have to worry about any cantilevers. And therefore, I've already sent you, so that your VF value is this and your MF value is that, okay? And like I said, so I've already sent you the sheet here, and this is for the long side, and very similar to what we did for the Gerber girder, okay? Except you only have one. Oh, it's taking a while, I guess. Here you go. So this here is the same thing. In other words, I have, this is the equation. I don't know if you guys want me to go over this again, as I did last week. This is the equation to calculate the ultimate bending moment of an unbraced beam, okay? These are all the variables that go into this equation. And on top of that, to get the value of omega 2, which is a load gradient, okay? Now, if you guys ever, if you want to putz around with this, okay, if you want to putz around with this Excel spreadsheet and you want to compare the values of this equation with the values in the beam load tables, okay, so take any value in the beam load table, right, put in all the right properties that that beam you're looking at, okay, and then as far as the L goes here, change the L to the corresponding L you see in the table. Just the only difference is that forget about calculating omega 2, put omega 2 equal to 1 here. Just make this equal to 1, and you'll see that the values that you get for MR from this spreadsheet is going to be exactly the MR values you're going to see in the beam selection tables. The only difference is that in that they're in that table is relatively conservative. They don't account for any gain in the what they call the omega 2 coefficient to account for increased moment resistance of the laterally unsupported doubly symmetric section due to the moment gradient. So what they do is they say the moment gradient in there is 1. So those values that you get from that beam selection table are on the conservative side. This is the more accurate way of calculating it. Like, since they weren't able to come up with 1 million tables because there's a different million gradient tables, if you want to be more accurate, you use the spreadsheet. Okay, if you use the spreadsheet to calculate the unbraced length of your of any beam, it's going to be more accurate than, or more precise than if you use the beam load tables. That's all it is. So here it is, and then again, like this mu value here, what you see here is calculated, okay, from this, okay, and the omega value is calculated up here in my spreadsheet. Now, depending on the value of mu versus the value of MP is what they call the plastic moment. In other words, that is the most you can get out of a cross section. In other words, the section modulus multiplied by the yield strength is called the plastic moment. That is the strongest resistance or MR value you ever get, okay? Now, if at one point this mu value that you get from this equation is greater than 2/3 that MP value, then this is the equation that calculates MR. When it's less than 2/3 or equal to 2/3, then this is the equation that calculates the MR. And of course, my spreadsheet checks right here. It does a check. And then on top of that, the MR value here has to be less than phi MP, which is it's just like phi. This is like MR is equal to phi ZX FY. That's what this is, phi MP. And of course, I also check to make sure, because sometimes this value can be higher than that, and therefore there's an argument in here that tells you this is the right value. And then the argument here looks at the value of here and here, and it tells you which one of the two governs, and it tells you. So here, for example, I have 169, and it all of a sudden, and it picks the right one, and it tells you what the MR value is. So what I did here is I told you to use a W 410 by 39, okay, as a trial section, and you can see right now that, wow, it's pretty strong, okay. It might be oversized for what you need, because I have an MR value of 172, okay, 172 here. And of course, what I can do is I can go and take something slightly lighter, okay. So what I did is I said, okay, so that's too strong. So I did a second trial. All I do is I copy this and I put on another sheet. I did a trial number 2, and I tried a W310 by 28, okay? And I put all the values for W310 by 28. And of course, this is simply copied and pasted from my ADA results. So this is what you should, when you do your ADA, you should basically be getting the same values of MX for, they're identical no matter which side you're looking at. You're going to get the right values of MX, and I just copy and paste them here. And of course, here, all of a sudden, this is too small. So what I want you to do on your own is, and I want you to do it, and I'm sure I did it myself. I want you to, excuse me, let me just, the one section, I think I even put on the sheet what I want you to try. Try a W360 by 33. In other words, go get all the values for W360 by 33. I'm sure it's going to work, okay, because I did it myself. So I in the Excel file, you'll have a third trial here, and I think I even put here, try a W360 by 33. Put in all the values for W360. Just whatever is in yellow is what you have to add, okay, and then the rest of the spreadsheet will calculate it. And if all of a sudden you see that it's okay, well, that's good. That means that will be the size of the beam that we're going to be using along the perimeter, along the long dimension of the building, okay? And it shouldn't take you that long to do, okay? So that's going to be for the long side. And then we do the same thing on the short side. On the short side, basically the big difference here is that the loads are much, much smaller, okay? Because basically it is just this part of the roof that's being carried by that beam. So you can see that the loads are very, very light, okay? And of course here, what happens is that they're not concentrated load. This becomes a distributed load along this beam, okay? And of course the geometry changes a bit. Like here we have 4.5 meter as opposed to 5 meters here. And of course this becomes a tributary width that the roof, you know, the load of the roof gets transmitted to this beam here. So that's the only difference. And of course, so now basically what you're looking at is that you're going to put, like, you have 1, 2, 3. So in other words, now the spans are 4.5 meters, 4.5 meters, okay? And that's, of course, that's because your wind column is here. And like I said, I always like to put a pin, roller, roller. If you put pin, 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 the answers are going to be very, very similar. As a matter of fact, if you guys want to play around with it, I do that sometimes. I put pin, 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 and then I don't put fix. Fix will definitely have a big change in the results. But if you put pin, pin, pin versus a pin, roller, roller, then you'll see the values are very, very similar. Anton, you have a question?
Yes, sir. For the slab, do we need to make a brand new ADA, or we use the same one we used for the lab 3?
Well, I mean, like every time you model a different geometry, you should start a new file.
Okay.
Why?
No, just.
Yeah, I mean, unless you want to screw up your Gerber.
No.
You know what I mean? Like, and like, I started a new file for the one in the long direction, and then if you want, like, you're gonna, like, I don't see what you're gonna gain by taking the long direction and trying to modify it for the short direction. I don't know if you're going to save any time, really, because then you have to go remove all the concentrated loads, put a distributed load. So is it really worth it? I don't know.
Yeah, thank you.
Yes.
Do we have to hand in these ADA with the final results, like these files?
No, like what I'm going to expect you to do is I'm going to expect you to, like once you've selected your beam, you're going to go back and put your beam in. You understand? You're going to put the right size beam. Like, for example, I told you try a W360 by 33 on the Excel spreadsheet. I want you to be convinced that it's a good size. So what I would do then, once I know that this 360 is good, I would go back to ADA, replace that 410 by 39 by a W360 by 33, rerun the analysis, and then I want you to take a picture of that analysis for shear, that analysis for moment, and that one for deflection. And copy those 3 diagrams and just put them into your design brief.
Okay, so this is for this perimeter beam.
Oh, for everything, even for the Gerber one. You understand? The Gerber.
Oh, okay.
Once you, like, for example, like I think we've decided that for the Gerber girder, I forgot what was the size of the drop-in beam. I don't remember, but we came up with one side. You guys had to. I asked you to work out 2 different choices for either the double cantilever or the left cantilever, and I told you try with the, and I don't remember, it was a W610 by 92. If I
Yeah,
think,
92. Yeah.
okay.
Yeah.
So what you should do now is take your ADA, okay, and go change all the beams and put the beams that you are now, okay, and you go check the deflection. And I'll show you how to check the deflection. It's very simple.
Okay.
Okay.
And we take snap
And exactly, in other words, you just do, you know, you go look at the results, you right click, print as a you know, a PDF, right?
Okay.
And then, you know,
And that also work. We have to do this for the Excel sheets. We have to also take the pages and put
the
them
Excel sheets, guys, I really don't care. You understand? Like the Excel sheets are there to help you design. You understand? So if you guys don't want to learn how to use them, it's like I'm giving you these so that it's simple.
No, I'm just no, it's not about that. I'm just making sure that what we have to hand in next, like.
Okay. In other words, what I want you to do is that once you try the W360 by 33, you understand?
Yeah.
You make a print of that sheet and you hand it in with your design brief. Yes.
All right. Cool.
But I don't want to see all the other trials. You understand?
Yeah,
I want to see your final choices. You understand?
Understood. Yeah.
And Omar, we're going to repeat this at the end of the semester just to make sure that you hand in everything that I want. You understand?
No, because I'm following step by step now. It's easier than the last.
Oh yeah, I know, and that's why I'm saying, like, if you do it like in other words, right now, okay, when I'm telling you that you should have your Gerber design done, is that I can go back and I'll show you my final Gerber design. Okay, I put in those things, and I'll show you what I did, but I'm not going to do it because I don't want people to take snapshots of my screen, and then they, you know, like, I want you guys to do it. You understand? But I went in there and I put in the those beams there, a W610 by 92, W610.
But would you tell us what's the deflection on, like, at least?
I can tell you that when you're going to check for deflection, you're going to take L over 360.
Yeah.
In other words, you take 10 meters divided by 360, and then you're going to go look at your ADA deflections, and if it's less than that value, you're okay.
Okay.
And I can show you, for example, I can show you that. I mean, I can show you that. I can show you how like I can show you how to do that on ADA. Very simple. That's where you have all those other, you know, like P1 with a factor of 1, P2 with a factor of 1, and then those are the ones you look at. Understand?
Okay. All right.
Okay. Don't look at the envelope, because the envelope is going to show you each deflection of each case, right? But you won't be able to see the values from the envelope. You're going to have to do each one individually. And I don't know if I have it here, or I can probably show you on one of my like I show you how I did it. You understand? So let's worry about now. So this is, of course, here, like I said, because it is a uniformly distributed load, you put a uniformly distributed load right across. Okay. And what is that uniformly distributed load? Well, it's your dead load multiplied by your tributary width, or your snow load divided by your tributary width. So therefore this becomes, you know, the tributary width here, of course, is very simple. It's half the spacing of your joist. So therefore this is the tributary width here is 1 meter. So therefore I multiply it by 1 meter. And of course, what this gives me is I have a superimposed dead load of 1 kilonewton per meter, and I have a snow load of 2.5 kilonewton. So this is not a very heavy load, okay, fairly light, and the spans are relatively small. So you should end up with something that is relatively small. And I can tell you that this is oh yeah, and then on top of that, what I did in ADA, don't forget, I don't show it here, but don't forget to add, okay, don't forget to add, if you want to get the same results, I still added a 1.5 kilonewton, because I understand I still added a 1.5 kilonewton here for the sag rods. Okay, I've added a 1.5 kilonewton. So here in the superimposed dead loads.
Is that as a concentrated load? On
Yeah, because that's what the sag rod does, right? It hangs right there in the middle of the span. You follow?
Yeah.
So that in other words, here's the beam that you're designing. Okay, this is the beam that you're designing. Here's a column, here's a column, here's a column, here's a column, here's the wind column in between, right? And here's one of the girts. I won't draw both of them. And basically, you make a hole here at the bottom flange, and you come and you support the girt. So therefore, it becomes a concentrated load on this beam. And then there's the other one, you understand? And all I'm saying is that I didn't show it here, but don't forget to, I showed it to you on the previous one. But if you want to compensate for that extra dead load that occurs right there, so I should show it to you here. So don't forget to add, okay, don't forget to add here somewhere, you know, don't forget to add 1.5 kilonewtons on your superimposed dead load to compensate for that girth, okay?
Okay.
Because I showed it to you in the long direction, but it also applies in the short directions. The only difference is that the girths are only 4.5 meters long, maybe the one, but add 1.5. It's safe. I think it's relatively safe. And I think when we designed the girth, if somebody reminds me, hey, maybe we should go back and check to see if we made enough allowance for these girths, and we can also come back and check it. But I think it should be okay. Fair enough? So like I said, so you put in your SID, put your distributed load and put also a concentrated load for the girth. If I'm not mistaken, the results you see here that I have here, okay, from ADA, yeah, I can see here how it kinks, and that's because of that concentrated load. And I'm sure I added that concentrated load here, and that's why there's a kink in my shear diagram right there. So. And of course, this is the bending moment. So a very small bending moment. And again, now your unbraced length here becomes 4.5 meters. And here's my VF force. Here's my, MF force. Now I sent you another file. It's the same file. I like to keep my files separate, in a sense. So this way I can look at the short beam. So I sent you this one here, right? Whereby I tried the W200 by 31. Is that what I asked you to try as a trial section for the perimeter beam? Did I tell you what to put for the perimeter beam as a trial section?
The trial, yeah, you did the last one. It was 200 by 15.
I like for the long side, I told you to start with a W410 by 39 and then ultimately try a W3 for the ADA. I told you to put a W10 by 39, right, to get your results to compensate for that.
For the short one.
For the short one, you start with a W200 by 31. I forgot to tell you that. Okay, so as a trial section, start with a W200 by 31. And like I did that. I knew I was on the conservative side because if you look here, you'll see that my MR value is a lot stronger than my MF value. So I know that this is a relatively good, understand? And like I said, this is I know that this is the moment from ADA, because if you looked at my moment diagram, I had 15, understand? So I know this is a relatively good size beam. It's way too good for the loads that it's being, has to carry. And then for my second trial section, I think I went down again. And for my second trial section, I tried still in the W, I went from 31 down to 22. And I felt that it was still very strong. Okay, so it was still very strong, and therefore I figured, well, can I go down even lower? And I believe that I want you to try, and I think on yours, I already gave you what I want you to try. I think I want you to try a W200 by 15 and see if it works. Exactly. Yeah, okay, so that's what I want you to try. So put in all the values here, and I'm sure it's going to work because I did it here myself. Okay, this is my file, understand? So it should work. And that's it. So now you've got your perimeter beams designed. And then once you've got now that you convince yourself that they're good, what we can do is, okay, so once you consider, then you check deflection. How you check deflection? You put the right size beam back into your ADA, and then you do one load case where you do 1.0 times your snow load. And then you check the results about bending about the MX axis, and you'll see what the deflection is. And if the deflection is less than L over 360, it should be more than adequate. That's how you check for deflection. And then once you've checked for shear, you go to you take that one there, the W 200 by 15, you go into the beam selection table, get the VR value for that. You don't even have to, because I didn't show you how to calculate shear for a beam, because it's all gets from there. And you take 80% of that, make sure it's greater than VF, and you check for shear. Everything is good. So this is, you're going to be showing your calculations, and that's it. So if you guys
Sir?
want, yes.
Yeah, would you mind open ADA and show us like a different example on deflections, like to remind us?
Yeah. I'm gonna do that right now. Not a problem. It's just that, as a matter of fact, I'm gonna open up Nermin's ADA. How's that? Because she had a question. I'm gonna open up hers,
Yeah,
and
why
then
not? Yeah.
and this way, like, so I'm gonna stop sharing here. Stop sharing this, and I'm gonna have to. Sorry, I'm gonna have to go and open up ADA. Or hold on a second. Nermin, everybody's going to see your hard work. Is that okay? You give me permission to use your file?
It is a hard work, but it's not working.
It
Please,
doesn't
Nermin,
matter.
please.
I like things that don't work. It makes us think a bit. You understand? I'm not worried about that, Nermin. I'm not worried at all. You understand? So let me see. I'm trying to remember where I put your file. Sorry. I know I put under my steel. I put under my steel. My steel. I probably put it under. Did I put it under labs? No.
And the funny thing, I did it twice. Like I went through the
Did I
pain
put it under
of putting
lectures?
all the.
Oh shoot! Where did I put your?
I can resend it to you.
Because you sent me your thing this morning, and I downloaded it, and I copied it somewhere. I'm trying to remember where I copied your file. Otherwise, I'd have to go back to my Mayo and open it from there. Trying to remember where I opened your file. Or because I don't remember the name of it. I don't remember. Oh, there it is. I found it. You just called it Steel Project. Okay, I found it.
Yeah, that's so creative. I know.
Okay, because I didn't remember exactly where I copied your file. I downloaded, and so here we go. Okay. Okay, so in theory, this is opening up. Hold on a second. So guys, don't compare your results to Nermin because she's, hold on, now I gotta go back to Zoom. I gotta go back to Zoom, and I gotta share this with you guys, and this way we'll all make sure that we are on the, okay, so Nermin, as a matter of fact, I might not even share my screen. I'm gonna just share your ADA because I don't have any links on this. Okay. Does everybody see the ADA now on their screen? Can I just have a yes, please, or no?
Yeah.
Okay.
Yeah.
Okay, so like I said, guys, now I don't know why, but Nermin, do you like having these axes in your face when you're doing ADA?
Absolutely not.
Okay, so what you do for that is you go to your visual. Okay, you can either do type O for your visual graphics, or you come here, and under the third tab, you just uncheck this global axis. You press OK, and it's gone. So now you don't have that ugly thing in your face anymore. Okay. Well, I look at your dimensions. They look pretty good. Your dimensions look good. Okay. And of course, everything looks good. You got the right end conditions here for the suspended, the drop-in one. Great. And as far as, let's go to, put this on members. Let's go look at your loads, your superimposed dead loads. They look great. Okay. So everything looks good. Now you're saying that when you run your analysis, you're not getting the same results. Is that what you're saying?
Yeah, the first member, it's acting like a cantilever, and I have no idea why. Because I have like a mom.
This one here is acting as a cantilever?
Yeah.
Okay, well, so let's go look at your load combinations. Okay, now guys, for your load combinations, definitely don't generate them because you're going to have 1,000. You understand? It all depends on. Okay, don't just okay. So great, you've got your ultimate limit states and you have your serviceability limit states, right? So now, so what you do basically, okay, you're ready to run an analysis. Okay, I'm going to run the analysis and see what happens. Okay. Okay, so what I'm going to do is now I'm going to go to, I want to look at your envelope first of all. Let me look at the strength. So there's your shears. Your shear seems to, I don't know if your shear, I don't remember the results, Nermin, so I don't know if it's good or not. But what do you mean, like the first one's acting as a cantilever? Let me go look at your moments.
Yeah.
Oops, sorry, save. Let me go look at your moments, results. Take this off. Let me look at MX. Okay, apply. Oh, yes, I see what you're saying. Okay, what you do here is, I see what you're saying. So in other words, this is what you're talking about. You're not coming to zero here, right?
Yes.
Okay, so that's because most likely, if I go back to your geometry, and if I go back to the reaction area here, okay, and if I go to supports, fix, and you have it fixed about the MZ here, so you have to free it. You have to allow it to rotate. Okay, so it's fix.
Is it the first one?
The very first one, yeah. The first one is a pin. It's not a fixed support. It's a pin. So how do you create a pin? You fix it in the X direction, you fix it in the Y direction, and you allow it to rotate about the MZ, the one that's perpendicular to the screen, because it's three-dimensional. Okay, and that's I can go check the rest of your supports, but I'm pretty sure that that's okay. I can go look at the rest of your supports. I have to zoom in. If I only have one yellow arrow going up, these are all good. And the way that you can check, Nermin, if you still have the red dot in here, that means you haven't released it. This was probably still red. I should have shown you that before, okay? Now, if I rerun the analysis, so that's the only problem, that you made that a fixed support, and of course, you did not allow this point to rotate, and therefore you ended up with a bending moment up here. Now, if I rerun the analysis, I'm going to save it. So that's the only change you're going to have to make to your thing. Analyze, close, and now, of course, let's go back to look at the envelope, okay? And you'll see that there. Is that better? And this looks pretty much like what I had, right?
Yeah.
Okay, so that was the only, let's call it, glitch in all your modeling. You didn't model your supports correctly, and I'm glad you did that, Norman, because I want everybody to realize how important it is that everything is modeled correctly, because she all of a sudden had a big negative moment here, which of course affected all her values. And at the same time, if that's how she analyzed it, she would have to build it that way. She'd have to make sure that that reaction is fixed. So she would have to fix the beam to the column. Otherwise, her analysis would be completely wrong. And that's, so Nermin, that was the only glitch you had. How's that?
Okay, perfect. Thank you.
Okay.
Can you look at the sheet?
Yeah. Now, as far as the deflections go, okay, what you're gonna do now is you're gonna go. I'm gonna first of all make sure I'm on the serviceability limit state. These are the deflections. Now, the problem with the envelope is that it shows you all the deflection, the maximum and minimum ones, but you won't see the values. Okay. So here is the worst deflection that you have. So what I'm gonna do now. What I'm gonna do now. I'm sorry, no, these are still the moments. Hold on a second. The deflection. So I take this off, okay? And I do deflections about the strong axis. Perfect. Press apply, and here are your deflections, okay? Now, if you want to go see the deflection here, you can click here, and it's going to tell you what the deflection is, okay, about the strong axis. And if you don't want to do it this way, okay, what you can do is you can literally, instead of taking the envelope, okay, take each different load case. In other words, take P1 under serviceability limit states. And what I like about it gives you the deflection here. Okay, so this is the deflection here. Now, guys, 10,000 divided by 360, how much is that? Oh, first of all, Nermin, is this still the W610 by, this is still the W610 by 125, right?
Yes.
Yeah, I think so.
Okay, so now what you do now, okay, so let's do it correctly. So now what I'm going to do is go back to my structure. Now I've designed my beams. I know all my beam sizes. So now what I do is I go back to my structure. I pick the beams. In other words, I go back to my structure. I pick one beam, and I pick another beam, and I pick this beam here, 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 and I pick that beam there. So those are all my W610 by 92. We agree? Yes, no, maybe?
100% agreed.
Great, okay. So now what I do is I right click, I go to properties, and I come here, and I go to steel. I go to my Y flange, and I go for a W610. So here's my 610s, and I go down to, I replace the 125 by 982. Fair enough. Press OK. And of course, I don't care about the material. And of course, I want to make sure that the dead load is included. So I make sure that dead is picked here. As far as the materials goes, I haven't changed it. It's going to stay the same. And I can just double check afterwards. So that's going to be for those. And now what I do now to make sure, I know my lengths are all good. So what I do now is I go here, I go to elements, I take off the length, I put shapes, and I put materials just to make sure I've assigned the right ones. So now there, so the materials haven't changed, but the shapes are good, okay? Now, what I need to do is for the drop-ins, the suspended ones, I pick here, and I pick there, and I don't remember what we said the size was. Does anybody remember the size of those? Does anybody remember the size of the drop-in?
I don't remember, not exactly.
Okay, because I'm trying to remember if I asked you to. Oh, you guys had to size that beam. You understand? You guys had to size that based on the fact that you had the MF and you had everything else, and you had to go to beam selection table. Okay, but I can tell you right now. So nobody sized that beam yet. That's what you're telling me.
No,
Did any-
wait. It was 4,000. 4,000. 4 meters, wasn't it? Yeah.
What do you mean 4 meters? I don't understand what you mean. I want to know what size you decided to make the drop-in beam.
Wait a minute. 1 second.
Because you had the MF value, you had the VF value, you had the unbraced length of 2 meters, and you had to go straight to the beam selection table and find a beam that's going to meet that criteria. If nobody's done it yet, well, I know what the size is. I have it. I've already have it here in my little calculation sheets. So I'm going to put one that is not the right size. So I'll let you guys worry about that. So I'm going to go pick something that's slightly different. I'm going to go pick something that's slightly different. Nobody's done that yet because nobody's given me an answer. I could tell you that you're on the right track. So
Wait, just to make sure, yeah, we are on the right track. I'm kind of lost right now because
well, like in other words, last week I showed you the results of, or the week before I showed you the results of the, in the lab I showed you the results of the ADA for the MF for the drop-in section. And I told you what the MF was, what the VF was, right? And I told you go through, and then I told you what the unbraced length was because the things are, and it's completely positive. So therefore you can go straight to the beam selection table and find a beam that meets the MR and the VR, and don't worry about deflection, so that you have the right size beam, okay? Deflection gets checked by ADA. And here on top of that, because it's a suspended beam, it's the deflection of that beam plus the deflection of the 2 cantilevers that you have to look at. So right now I'm gonna pick one. I'm gonna put one in. I know that's, yes.
So the thing we did on XL, what was that?
That's only for the girder. That's for the girder with the left cantilever and the girder for the double cantilever. That's all you did. You had to go in and size the drop-in beam, which is the easiest one. It's just like all the beam problems that we've done in class. You've got your MF value, you have your LU value, go pick a beam. What more can I ask you to do? You understand? So like I said, I'm going to put one that I know is not the right size. Okay, I'm going to go for a W530. I'm going to put something that's, so I'm going to put something 530 by, let's say 85. I know this is way too strong. I'll put this here. Don't come as, if you put this as your solution for your drop-in, I can tell you I'll mark it wrong because this is not the right size. It's oversized. Press OK. So if nobody tells me, I know what I have. I've done it. Okay, I went to the beam selection table after I got my results from ADA, and I was able to go and select the beam. So I need to know the answers to that one.
Okay, sorry. Okay, I'm sorry. You can continue, but the thing is, I'm not sure what's a drop in. I'm sorry, but I'm not sure what's a drop in.
The drop in is the one that's hanging on the 2 cantilevers. I'll go back and I'll show you. Well, let's go back. Let me first put this one in. Okay. Let me put this one in. Oh, sorry. I want that the steel doesn't change. I just want to make sure I have the dead load included. Okay. Okay. So basically, if we go back and we look at the results, right? W550 by 30. Oh, I don't have the materials assigned to this yet. So I have to go assign the materials. Otherwise, I'm going to mistake for the, I have to go assign the materials because I screwed up. So the materials, steel, ASTM A922, and of course, calculate the dead load. Okay, so there you go. So everything's been assigned, and that's what's good about looking at everything on your screen. So if I noticed that I hadn't assigned material, if I was going to try to run the analysis, AD was going to tell me material is not assigned, and therefore I have to go back and check it and change it. So now that I know everything is good, I can take this off. Now, Omar, go back to what we're saying, okay?
Okay.
If I go back to the results here, okay? So now I have to rerun the analysis because I changed things. So AD, as I'm going to rerun the analysis. Now, the results are going to be slightly different because I put in lighter beam. So therefore, your MFs are going to be in the same order, but they won't be exactly what you saw the first time. So here you go, analyze. And it says calculations are complete. I can close this. And of course, I'm going to go back to the envelope and I go to, okay. Ooh, I don't want to see the deflection. Those are the deflections, but now we want to go look at what you wanted to see before I come back to the deflections. I'm going to go look at the results regarding, this was for deflections, and this was MX, okay? Apply. So Omar, this here, okay, where is that, where's my annotate, okay? This here is the drop-in beam. You understand? This here is the drop-in beam. What's the MF value?
155.71.
It's a little bit less than the other one because the other one, we had a heavier beam, you understand? But it's in the same order of magnitude, right? So just because, like, this is what's happening. Here's my column. Here's my column. Here's my cantilever. And here, this is a drop-in, okay? So the drop-in is as if it's sitting on a pin, and it's as if it's sitting on a pin because it's a pin connection. So basically I only have a positive moment. So therefore it's just like designing a beam that has a span of so much. So instead of you having this is the span, here are my loads, here are my different combinations, let me do my MF value. Well, 88 tells you what your MF value is. So this beam has to resist 155.7 kilonewtons or whatever it was like before I modified it. So now there's my MF value, and then I go to the beam selection tables. I know that my LU, in this case here, I have joists at every 2 meters. And since it's only the top that's in compression, it's fully supported by so therefore my LU is 2000. So I have my LU value, I have my MF value. I go into the beam selection tables and find a beam that will meet this criteria.
Okay. Okay, I see. Okay. So the LU is 2000. Okay.
Yeah, because isn't that where the open web seal joists are resting on the beam?
Yeah, they are. Yeah.
So that's what I'm trying to make you understand. That's why I do projects, so you guys can see, oh yeah, I have these members that are running perpendicular to my span, and those are laterally supporting, and it's just the top that's in compression. So the whole top flange is being laterally supported. Therefore, the LU is that spacing in between those members, and that's my LU. Now I got my LU, I got my MF, beam selection tables, find a beam. Don't worry about the IX, don't worry about the VF, because then you're going to put in here, or you can check your VF while you're there, and I'm sure it's going to work. And then when it comes to deflections, you don't worry about it. Okay, when it comes to deflection, you put that right size beam into your thing here. Like here, I told you, you put the right size beam in here. And now you notice that the moments have changed slightly from before. I don't know if you guys can see this, but they've changed slightly. Why? Because the beams are a little bit lighter, and therefore, and then if I want to become really religious, I should go back and take these values from this year, put them back in my Excel spreadsheet, and I'm only going to get better results than before if I really want to get religious about it. But I won't do that. Now, once I've done this, then of course, now what I'm going to do is I'm going to change this to deflections. Okay, I'm going to deflect along the strong axis, apply. So the only problem is if I look at the envelope, I don't see the values here. Okay, so here, what's nice about the envelope, look, at one point, depending on the snow load, the deflection is upwards, it's not even downwards. Okay, and of course, this is where you have 100% here and only 50% there. That's that. But if I want to see this, what I would do is I look at the individual loads. So in other words, I look at the very first one. Okay, so a P1 service load. Oh, here we go. And like I told you, this was the first one. And you can tell that this. So here, I look at the maximum deflection. The maximum deflection here is 17.3. Like here, as a matter of fact, it deflects upwards. I don't worry about that. Here it's 2.5 and so on. So therefore, I take L over 360. So, and then what I would do is I would, okay, so what I'm going to do now, once I have all the right member sizes, okay, and I L over 360, 10,000 divided by 360. Does somebody have a calculator?
27.8.
27.8. Okay. Does it exceed 27.8 anywhere along my diagram? The answer is no. So for case number one, perfect. Okay. So you clear this. Okay. So what you do, once you have this done, you right click, you say print. So you print to a PDF. Okay. And you file it away. And you got your deflections for P1. And then after that, that's okay for P1. Oops, sorry, I shouldn't have done that. Like now it's gonna, I'm just gonna save it here. I don't care. So you save it. Okay. Then after that, what you do is you go to P2 and you look at the deflections under P2. So serviceability limit states P2. And there it is. Oh, look, nothing exceeds 27.7. I'm good for P2. Right click, print, and print this one. And then at the end, guys, if you want to make it really nice, okay, you go to the lab, right? You take the PDF editor in the lab, -2H27. If you don't want to have thousands of sheets, okay, you can combine these all into one PDF and then just put on one sheet. It's going to save you, you understand? But it's up to you. And then this is the second deflection. And then after that, I do the same thing for deflection number 3. I go under serviceability limit states. For number 3, oh, still good. I don't exceed 27. And what's nice about ADA, guys, this cantilever here that goes down, believe it or not, the deflection that you see here also adds the deflection caused by this cantilever. Okay, that's what's nice about ADA. So it's got the deflection caused by the beam plus adds the deflection of the cantilever, and that's why it's down to 7 point whatever it is down here. So at no time do I exceed 27.8 here. I'm okay for case number 3. And then I go to case number 4, same thing. Oh, 12.3, still good, still very good, still very good, still very good. So as far as L over 360 is, these beams are stiff enough. And that's the best way to do it.
And for when we do the selection for the drop in, do we choose the lightest one?
You should, yeah.
Okay.
I mean, the light, always choose the lightest section. You understand? What we did with the W610s by 92, we even went to laterally brace them so that we can come down and choose the lightest section possible. You understand? And that's it. So there's your deflection check. Okay. So once you size the member, you go back, put the right member size in ADA, you run your analysis with the right member sizes, and then you just check, you know, SLL, you know, service load limit states P1, P2, P3, P4. And if at all, and like you should be getting very close to the results you saw here, because that drop in I put in there is in that order of magnitude of what you need to have for your project. Okay. So Norman, we found a glitch in your thing. I hope you're happy. I hope you're able to change it.
Absolutely.
Okay. And I'm going to stop sharing this. Now, guys, I am here to help any and all of you. So if anybody like Rania, are you there? I don't hear her anywhere. I guess she's not there. But does anybody want me to do anything with their ADA, whatever? Because we can share screens. We can, if there's anything you don't understand on the Excel spreadsheets, we can share screens. I can show you what to do. Or is everybody feeling good on what they have to do now? Because I'm going to just spend the next 30 minutes and so to help anybody on a one-on-one if they need to. Understand?
Sir, I was
Yes.
looking for the file that you sent me, and I found an error in
In my
the
file.
ADA. Yeah,
my-
do you mind if I share it?
No, by all means, if there's an error in my file, we'll correct everybody's file and make sure that it's all corrected. I appreciate that. You understand? Like
Yeah,
I told you,
perfect.
I could have easily made a mistake. You understand? And I'm going to, hold on a second. Let me just stop sharing this. Okay, let me just make sure that multiple participants. And so go ahead, Alex. We can share. Okay.
Okay. So this is your share,
Yeah.
and the error was right here. This 249.
Okay.
So when I went to the loads, I went on all loads, and if you check here, you placed a load 45 in the incorrect spot. It should be on the 10-meter span. So when I did it myself, let me switch. So when I go to my loads here, this is my file right now.
Okay.
On this one, I just placed them here, and the 45 is on this one, which I believe is correct. And this is what I got. So it's a lot smaller.
Okay. So what you're saying is that on my file, let's go back to my file. Okay.
Okay.
Okay. Let's go back to my file.
Should I go on the share?
Yeah. Let's look at the shear. Well, I mean, like, let's look at no, let's look at the loads. Okay. I just want you to
Okay.
appreciate one thing. Okay. Let's go to loads. Okay. Now, I want everybody to appreciate this. Okay. Is that when it comes to, let me just see if I can, I think I'm going to have to ask to share, request remote control. Okay. So that we can talk about this. So I think, okay, so I'm good now, right? Yeah, okay, good.
Yeah.
Now, here, the load that I might have misplaced is right on a reaction area. Can everybody see that?
Yes.
See that that's a reaction area here? Okay. So this will not affect the bending moments whatsoever. It's going to affect the shear value, and it's going to affect the axial value for the column. So, okay, so that's number one. Okay. And if you want to be more precise, I know what you're saying, Alex. Like so, because what did I do here? I put a 45, and what did I do in my loads that you found that I did incorrectly?
You on your snow load P3.
Yeah.
You placed the one of the loads on the, I believe it's a 2.2 meter member, which should have been starting on the 10 meter member.
Okay, so you're saying it's on my loads. Okay, so is this my file?
Yes.
Okay, so in other words, if we go to loads here, if we go to loads, we are at loads here. So you're saying as far as P3 goes, P3, okay. So this is what I did for P3. I put 100% on the first two spans, and then
Yeah,
I
so
put
the last 45 should be on the next span over.
on this one here.
Yeah. And I believe it would stay as a 45.
Pardon?
Right.
45 is 100% snow load, right? Yeah. And 22.5 is 50% of the snow load. We agree?
Yeah.
Okay, so we said that we put 100% on the first two spans, right?
Yeah, if you select that one right there,
okay,
the member, that 45 on the right should be on the next member.
On this one here.
Exactly. That's the issue that I'm incurring.
Okay, so
if you look at all the other snow loads, they're all on the next member over.
Okay, so what you're saying is that here I started at 2.
Yeah, so you should start at 0.
Okay, okay, so I should start at 2. Now, why do I have it twice here? I don't understand that.
I've been encountering that too. I think it has to do with the either the load cases or the combinations.
Okay, but it doesn't double up the force, because otherwise we'd see it, both of them added on. Okay, so here I put it at 2. Okay, and then for this member here, and then I put it at 2.2. So here I put it at the end of this member, right?
Yeah.
And then after that, I started at 2 meters away.
Exactly.
So you're saying that I should have put 45 on this member here.
Yeah.
And then not put anything here.
Exactly. Because I believe if you look at your other snow loads, that's the
how
same
I do
pattern
it.
that you follow.
Okay, that's the pattern I follow. Well, okay, well, in that case, let me go and, so what you're saying
I
is
did
that,
the same error when I first started my ADA, and that's the exact issue I was having. My moment were perfect, but my
Okay.
shear were all off.
okay, so basically what I can do is I can say delete this. Then why doesn't it remove it here also? That's what I understand. I understand what ADA did here. Delete this. I have nothing there, and I come back to this one here, and at 0, I should add minus 45. Oh, how come it's not going in? Minus 45. Oh. Oh. Minus 45. Wow, it's not allowing me to add anything here. Why?
Here, I could try it.
Oh yeah, okay, there you go. Okay. Just press OK. So that's the change we made, right? And now you're saying that when we run the analysis, it's going to affect the shear.
Yeah.
Wow. We won't get the same shear value. Is that what you're saying?
Exactly. It should be like, instead of 240, I think it's like 188.
Okay. So close.
Alex.
Yeah.
Did you put the new member though, the 610 by 92?
No, this is the previous one.
Okay.
Okay.
Just want to make sure.
So now we're all talking the same page. Now, in theory, if I go to my strength.
Exactly, 180.
Yeah, but then down here is 277.
Yeah.
It's just it's the same shear. Do you understand? All it did is that it reversed it, but it's the same shear value. See, you guys have I understand. Okay, now I understand what you're saying. We have a different value. No, what we did is that we changed on, like, in other words, it was 277 up here,
No,
and
I
now
believe the 277 was there before.
Exactly. All you did is that you reversed the shear. But the shear value is not minus 277, 183. In other words, when I'm looking when I'm looking here, Alex, for this member here, okay, the highest shear value that I have for this member here is 277. So whether I see it up here or I see it down here, it's still 277. So you understand? It's like you're absolutely right. Like, in other words, if I put it on one member, it's going to go
but
below.
I believe
if
on top it was 240.
Pardon?
I believe on top it was 240.
Was it 240?
I believe so.
And then ultimately, Alex, what you have to keep in mind is that since this is a W 610 by 92, this is also W 610 by 92 and W 610. Since I have to design for this shear here, once I design for this value, it covers all the values here.
Yeah.
So
yeah, I just wanted to make sure that was fully correct.
And I think I understand what you're saying is that all it did is that it brought the shear from this side and it brought it down to here. So in other words, it reversed it and it brought it down to here. I understand what you're saying. Okay. Well, but I'd have to check with my results. I think it was 277 here anyways, if I'm not mistaken. Like, it was up here because I had put the load on this member. But as far as VF goes, if I was looking for, if this was a totally different beam that I would be using, this is the VF value that I would use for that beam. Understand?
Exactly.
Okay. So, oh yeah, okay. I appreciate what you're saying. So ADA will like change the position of the shear based on which member you're loading it to. Interesting, right?
Yeah.
That's interesting. Thanks for pointing that out.
All right. Thank you.
Okay,
I'll
so
stop sharing.
we're talking the same thing, but you got it on top because you put you were following the pattern more religiously than I was, and okay. But as far as the end results, we're both talking the same thing, Alex. I hope you appreciate.
Exactly. Yeah. And the
Okay.
calculations are the same results.
Exactly. So that's great. So thanks for pointing that out. But it's good to know that ADA will like the way it will display the shear. It depends on which end of the moment. Like you know what I could have done, Alex, to make my life absolutely sure. Okay.
Yeah.
Is that all the ones that fell on the reaction areas, instead of putting them on the members, I should have put them on the nodes.
Okay. Yeah.
I could have done that, and then it wouldn't have made any difference. We would all have the same shear diagram. Understand?
Yeah. Sure.
So I'd be curious if we did that. Like remove it from the member, put on the nodes, see what happens. How does ADA handle that? But that's I'll try that one day just for my own satisfaction. But thanks for pointing that out. Okay, so that ADA will, I guess that's how the program, the algorithms work, right? It kind of like looks at it like right over and then it drops down because I understand now what's happening. Okay, thanks, Alex, for that more insight on this program.
Thank you.
So does anybody else have any questions that we can talk about? Guys, I hope you're having fun with this. I am. So is everybody good? Does everybody know where they're heading, or is everybody still like, because like guys, like if you are lost, don't be embarrassed. Now's the time to ask the questions. There's no stupid questions at this point. I will help you to make sure that you.
What would we need for the like the final project? Like we have screenshots of the ADA once we placed in our new members. Correct?
Yeah, and then for example, once you've selected your, you're gonna have to show me on your calculation sheet what your MF was and what your VF was for your like the drop-in beam, the suspended one, right? And then you're gonna have to show me like what member you chose for that, and then it's all on the PowerPoint. And then as far as you're gonna have to go show me what your VF value was for that beam and what your VR, what you calculate for VR to be. You understand? And it's just like basically the assignments. So it just
once we choose the member, do we also have to show the ADA screenshot of
the
those?
ADA screenshot is to show me where you got your forces from. You
Okay.
understand?
Yeah.
That's in other words, that like like in class, what we do is do MF is equal to WFL squared over 8, the VF. Okay, so that's all done. That analysis is done with those beam formulas. But here we have an analysis program that does that for us. So I want you to show me where you got your forces, and and then from there, you designed your members accordingly. You understand?
I believe last class you told us to show the Excel file, but this one you don't want to. What do you use the Excel file?
Like just show me the last trial. In other words, show me that when you tried the W610 by 92, that according to the Excel sheet that I sent you, it was okay with laterally braced at 4 meters for both the left cantilever and as well as the double cantilever.
Okay, and once we find our final shape, do you want to see the deflection?
Oh yeah, then that just confirms that shape, it has the strength. Now you have to confirm that it's got the serviceability. And how do you check serviceability? Well, you're not going to go through the whole trouble trying to calculate the deflections of that double cantilever. That's quite intense there. Okay. Yeah. So what you do is you take your profile that you decide that has a strength requirement. In other words, it has the MF, has the VF, and now the moment of inertia is already in ADA. So therefore, you just put that shape in your model, because now you have the exact shape that you want to use, and let ADA calculate the deflection. And that's why, as far as the load case goes, you just put the snow load on there. No dead load, no factor load, just 1.0 times your snow load, and then you see how it deforms under ADA.
And would you like a screenshot of that?
Yeah, exactly. I want a screenshot of the 4 load cases to show me that each load case, the deflection does not exceed 27.8, whatever it was that somebody told me was around 28 millimeters. You understand?
Okay, so we're gonna have 4 screenshots of the deflection for each load case.
No, you only have 4 screenshots. You only have 4 load cases. You have P1, P2, P3, P4.
Yeah, so 4 for the deflection.
4 for the deflection for the left cantilever, 4 for the deflection for the double cantilever.
Okay, perfect.
Okay, so in other words, you'll have 8. And if you want, I don't know if you ever done this, but if you take the PDF editor that's in the lab, you know, you can combine all these into one page if you want. You understand?
Yeah.
And instead of having 4 separate pages, you can have them all on one page, and it's going to be much easier for me to, you know, it's much nicer. That's what I did when I think I showed you that. Let me see if I did that. Let me see if I did that. Hold on a second. I didn't do it here, but I think I did it. I think I did it for the other PowerPoint. If I open up the other PowerPoint, you'll see that I've combined all 4 deflections on one page. You understand? So, or what you can do is you can like, I don't know if you know, like, you guys know. Oh, okay. You guys know how to take a snapshot of a PDF, right? I don't know if you can do that. You take a snapshot of PDF, open up a Word document, take your snapshot, and then just copy it on your Word document. You understand? I think that's even easier than if you use the PDF editor. You understand? Just copy. That's what I do with the PowerPoints. I take my ADA, and then I go and I make a snapshot of it, and I put it on my slide. But you know, you can do it on a Word document if you want. You understand? And this way you can have all 4 of them, one below the other, on a Word document. And then after that, of course, you can convert your Word document into a PDF. Understand? Or maybe you can, you know, like, it's up to you. Understand? So as far, yes.
Sir, I have a question.
Go ahead.
So I got the drop-in selection. I got like W250 something. Like I can tell you the whole.
W250 by what?
I'm gonna tell you 1 second. It was W250 by 33. I'm sorry. By what? By
39.
39.
W250 by 39.
Yes, sir.
Okay, so let's go look at the beam selection tables and let's see if you did it right. How's that?
Yeah, sure.
Okay, let's see if I have the beam selection table open here. Okay. Okay, so let me share this with you. Hold on a second. Okay, so let's go and share the beam selection tables. So Omar, does everybody see the beam selection table?
Yeah.
So you said that you ended up having a W.
250.
Okay, so W250, here's my W250 by, let me just, go ahead. Tell
39 by 39.
me, just point, like, I think I shared the screen with you. I think you can.
Yeah, I can. Yeah, 1 second. I'm sorry. Yeah.
Go ahead, show me what you did, and I'm gonna look at your work now, and I'll let everybody else do it.
Okay, so 200 by
just draw a line where what you picked. You said W200 by 39.
Oh, sorry. That's 1 second. Let me undo that. I'm gonna redo it.
It doesn't matter. Omar.
Yeah, that's it.
Okay, so what was our MF value?
It was 156.
Okay, so you end up with a W250 by 39, and
yeah.
Okay, and what was your and you, of course, your shear should be more than adequate, because I think you had like 90 something for shear, and if you take 80% of 300, that would be ample. IX, you don't care because you're going to be doing it. So not a bad choice, but I would have selected something else.
There's a better choice. Oh
no, I would have selected something else.
I mean, the second choice I saw would be this one here, but I think this would be a little bit big here.
Which
this
one?
This is
okay.
The second choice.
That would be your second choice. Okay. What about going above that to what's in bold?
The 39. This one?
Yeah. Why don't you go for that one?
But isn't that too? Okay, the same price. Oh, okay.
You
The
see,
same weight.
it's same weight. So you're going to be paying the same amount of money. The only difference is that you're going to have a better moment of inertia. You're going to have a better shear. You understand? So
Okay, I see.
So
like
you picked that one because VR and IX is bigger. Okay, I
the
get it.
IX is bigger. So, you know, like
Yeah.
you're paying the same. Like, guys, I told you this, right? Like, if you, when you come to the beam selection table, look what's bold. You understand? So, for example, if this was higher, like if this, like, why did you go for this one, and why didn't you go for this one, W360 by 33? Oh, because your LU here was too small, right? For 2000, you didn't meet the MR value. Is that it?
Yeah,
That's right.
exactly.
Okay, that was a problem. Okay, so therefore that's why you decided to. But now you see for this one here, is there any reason why you didn't go for this one? It's the same weight.
I was looking at the MR value. To be honest, I was looking at how close it could be towards the MF.
Yeah, but
So
no,
that was,
remember when you come to the tables, the first thing you worry about is this column here.
Yeah.
Okay, so you look at the MR value that is going to give you bigger than the MF value. Our MF value was what, 157 or something?
Yeah, 156.
156. So therefore, I know that this is no good here. Okay, this is good here, but for this beam here, when I go up here, this would be I have a good MR value here. I have a good IX value there. You understand? I have a good VR value. So Omar, good choice, but I think that this would be a better choice than.
Okay, thank you, sir.
You see what I'm saying? So Omar, very good. Like
Yeah.
you did, everything's perfect here, what you did, except that if you look at it a little bit more and see what are my other options, is there anything up here that, so here, all of this is bad because these are all heavier than what you chose. Okay, so that's not a good choice. But if I look at this one here, that's the same weight as what you chose, and I go look at the value here, oh, look at this, right? You understand? So look at, oh, look, I get even a better resistance, I get better moment of inertia, and everything weighs the same. So why don't I go for this one as the choice for the
Okay.
drop-in beam? You understand?
Well, that makes sense. Okay, thank you,
It
sir.
all makes sense now, right?
Yeah.
So I totally agree with you with that choice, Omar. So you're starting to get the hang of how to use these tables a little bit more efficiently, you understand? But good choice. I like the W250 by 39. I'm pretty sure if I put that one in, Omar, we're going to get very, very similar results. The only difference is that the deflection of that one is going to be slightly higher than the W410 by 39. Understand? That's the only thing that's going to end up having. But because they're exactly the same weights, I'm going to get the same MF value, the same VF values from my DA. The only thing that's going to change is the deflection. And it's not going to be that much of a difference because if you look at IX here, it's 120. Oh yeah, it's going to have a good. It's going to have a good difference in deflection. So it might have a problem. You might. I don't think you have a problem with your deflection, but if you can put a stiffer member, the better it is. Okay, so I agree with you totally, Omar, with your
All
choice.
right.
Do you agree with my
Okay.
choice?
Of course, yeah. But first I didn't understand why you chose it, but now it makes sense.
Yeah, exactly. Like in other words, like I too, like I said, I come up here, I come here and I come here and I worry about this is where I am. I come here. Oh, here. It's good. So I can go across. Oh, no good. I'm sorry. Oh,
Yeah.
here there's a blank. So let me go look at the MR value here because the LU is 115. Oh, good choice. Okay. And then
Okay.
before I decide on something here, I always look right above it, see if there's anything that might help me. Okay. And in this case, it does. You understand? It does.
Okay.
Because it's just a coincidence that this one happens to be exactly the same as that one, Omar. It's just a
Okay.
coincidence, you understand? But it's a very good choice that you made. You understand? Nothing wrong with it. Okay.
All right.
Okay.
So, sir, you might have repeatedly answered this question. So once we have the drop-in beam, we put that in our other ADA file, And
You
then
put in the ADA file that you model your whole Gerber girder and
Yeah.
put that size for the drop-in beam.
Okay.
Okay.
Yeah.
And at the same time, change also the ones for the other ones. In other words, all the other ones where we put a W610 by 125 and change those to a W610 by 92. Okay. Because those are the ones that we've designed.
Right.
Like, you know, so like I told you at the beginning, I always tend to put something a little bit heavier than what I have. Like, you know, even for the drop-in beam, I made my life simple. I just put in a W610 by 125, and I knew that that was going to be way oversized.
Yeah, for sure.
But I didn't care because I just want to compensate for the dead load.
Okay, fair enough.
Fair enough.
Thank you, sir.
And then you just like, and then as you're finalizing your choices, you put all those choices back into the ADA, and now ADA, you run the analysis, and that's going to be your final. Like what I have is for example, I have what I call my ADA preliminary. I left that. Okay. You don't have to do this. And I also have an ADA final. Okay. And now if you look at your ADA final, okay, what I even did to be even more accurate at the beginning, I just assumed that at the two columns at the end, I just took half or whatever it was, and I put that on because I just wanted to make sure that I compensated for more than what the columns were going to carry. But what I did is that when I analyzed the perimeter beams, okay, I went and I took the reactions where those columns are, and I modified the values of ADA, the loads on ADA. And I'll show you that when we do the columns, okay? But that's just tweaking. But if you don't change it, it doesn't matter. You're just going to be that much more conservative. But I don't want to confuse you, but that's what it is, okay?
Yeah.
Okay.
Yeah.
Yeah, sir. A quick question. If
Somebody had a question on wood. Are we finished with steel?
yeah, that's me. If they're finished with the steel, I have a question.
I don't know. Does anybody else before you steal their time?
Yeah.
Does anybody else have any questions on steel? Rania, are you there? Because I've been calling her out a couple of times. I don't know if she can hear me, but I know she sent me an email and I answered her, and I just want to make sure she's okay. But I don't know if she's there or, you understand? Okay, so since nobody else has any questions, go ahead, Omar. Ask me your question on wood.
Okay, sir.
Cool.
So,
Let me put this on pause because it's got nothing to do with steel. I'm going to pause this.